You see a rocket launch, right? That incredible pillar of fire lifting off the pad.
Yeah.
It's just awesome.
It really is.
But it's easy to just see the power of the spectacle. Have you ever really zoomed out and thought about everything else, all the stuff that had to happen just to make that one moment possible?
Oh, absolutely. It's kind of mind-boggling when you actually stop to think about it. It's not just building a machine. It's, well, it's the end result of so many design choices, incredibly precise manufacturing, a global logistics web.
And rules. A whole stack of regulations.
Exactly. As tall as the rocket itself sometimes.
Right. And that's what we're doing today, our mission, if you will. We've got this huge pile of sources, articles, technical docs, industry reports, and we're going to unpack that whole almost unbelievable journey, getting something from here on Earth all the way to orbit.
Yeah, we're basically tracing the entire life of a rocket, from the very, very first idea, right through to launch, deploying the payload, and, well, what happens next?
We'll look at the whole ecosystem, this global network that builds these things, the insane logistics of just moving giant parts around.
And the rule book that governs it all. Because operating in space and getting there, it's one of the most demanding things humans do.
So think of this as your shortcut, your way to really get what that flash of light and thunder actually represents.
Okay, where do we start?
Well, it all begins, maybe surprisingly, not with metal or fire, but with a question. A fundamental question. What are you actually trying to do in space?
Precisely. That's phase one, concept and design. Before a single part gets made, you have to define the mission. Are we talking satellites? Big ones, small ones, thousands of them.
Right. Or is it cargo for the ISS? Or maybe even people?
And that decision immediately starts locking things in. Critical requirements just flow from that.
Like how heavy is the payload? How big is it physically? And where does it need to end up? LEO, GTO, maybe SSO.
Or even further out, lunar orbit, Mars. Those have huge implications.
And tied right into that is the business side of things. How often do you need to launch? What's the budget? How much can it cost per launch?
And the huge question driving so much innovation right now, is this rocket going to be reusable? Because designing for reusability from the get-go, like SpaceX did with Falcon 9 and Starship, or Blue Origin with New Glenn, it changes everything.
Okay, so that mission definition leads straight into feasibility studies, the big trade-offs. This is where the really core engineering choices get made, the ones that shape the whole vehicle.
Absolutely. It's where the debates happen, like propulsion. Do you go liquid fuel or solid? Which specific engines are best?
Our sources mentioned a whole family, right? Merlin, Raptor, BE-4.
Yeah, RS-25, Rutherford. Each picked for its thrust, its fuel, its performance profile.
And how many stages? How many pieces will it shed on the way up?
Yeah.
2, 3. Or are you aiming for that holy grail of single stage to orbit, which is incredibly tough? Then materials. What gives you the strength you need without weighing a ton? Is it the tried and tested aluminum lithium alloys? Or maybe those cutting-edge carbon composites, like Firefly Alpha uses.
Or even something totally different, like the stainless steel SpaceX is using for Starship. That was a bit of a surprise initially.
Definitely. And then you've got aerodynamics designing the shape so it flies straight. Structure, making sure it doesn't just vibrate apart on the way up.
Don't forget the GNC guidance, navigation, and control. That's the brain, basically. Telling the rocket where it is, where to point, making those tiny adjustments constantly.
All of that architecture gets hammered out. And this phase usually ends with something called a preliminary design review, a PDR.
Right. It's basically okay, does this plan actually hold water? Is it feasible before we start spending serious money? Checkpoint.
Gotcha. Plan approved, PDR passed. Now you actually have to build the thing. That takes us to phase 2, detailed design and fabrication, tuning the blueprint into actual hardware.
And this is where it gets incredibly detailed. Every single part, down to the last nut, bolt, and wire, is meticulously designed. And then you have to figure out how to physically make it.
Which involves specialized manufacturing. You often need custom tools, custom jigs, and fixtures just to handle and assemble these huge, complex components.
Think about welding those massive fuel tanks. You mentioned friction stir welding for the SLS core stage. That's a highly specialized process. Or machining engine parts to tolerances measured in microns.
And we're seeing more advanced techniques too, right? Like Rocket Lab using 3D printing extensively for their Rutherford engines.
Yeah, that's a big one. Additive manufacturing lets them create really complex internal geometries for injectors and pumps, things that are hard or impossible to make traditionally. Plus, it speeds up prototyping.
And others are laying up carbon fiber composites with robotic precision, building the flight computers, writing literally millions of lines of flight software.
Forecasting the huge segments for solid rocket boosters. That's a whole different process again.
And woven through all of this manufacturing, quality control, it has to be relentless.
Absolutely non-negotiable. It happens at every single step. You hear about standards like AS9100, which is the quality management system for aerospace, or NADCAP for special processes like welding or heat treating or composites.
These aren't optional. A tiny flaw, a missed check here, could lead to disaster down the line.
Precisely. So all this detailed design work, the manufacturing plans, they get scrutinized again in the critical design review, the CDR. Pass that, and you're really ready for full-scale production and assembly.
Okay, so CDR passed. Now we move to phase 3.
Yeah.
System assembly, integration, and test. Putting all those carefully crafted pieces together.
Right. Subsystems start coming together, engine parts become a complete engine assembly, avionics boxes get wired up and integrated into the structure.
And then comes the testing. So much testing.
Oh, yeah. Testing, testing, and more testing. It's mantra.
You test components individually, then you test the integrated subsystems.
Hmm.
Engines go on to test stands for full hot fire tests.
Hmm.
We hear about specific sites, right? Like NASA's Stennis testing the big RS-25s for SLS.
And SpaceX's site down in McGregor, Texas, which is just incredibly busy, apparently running multiple engine tests almost every day, firing Merlins and Raptors constantly to verify performance and reliability.
Then you test the whole stage. Structural tests push and pull on it, harder than it will experience during launch to make sure it won't buckle.
Pressurization tests check for leaks in the tanks and plumbing. Avionics tests make sure all the electronics talk to each other correctly, that the software runs as expected.
And the big one for liquid-fueled rockets, the static fire test.
Right, on the actual launch pad. You bolt the rocket down, fuel it up, and fire the first stage engines for a few seconds. It's the ultimate dress rehearsal, verifying the rocket and all the ground support systems are truly ready.
Assuming it passes all those checks, you finally stack the stages, usually right there at the launch site.
Yep. Then you carefully lift and mate the payload, the satellite or spacecraft on top, and enclose it all in the protective fairing.
And then one last round of checks. A series of launch readiness reviews, or LRRs. Everyone involved, from engineering to safety to range control, has to give their final go.
Only then do you proceed to Phase 4, launch operations, the main event.
This is the part everyone sees, but even this is a complex sequence. First, you have to get the assembled rocket to the pad. That might mean rolling it out horizontally and then erecting it, or moving it vertically on a giant crawler transporter.
Then comes fueling. This is often done quite late, especially for cryogenics like liquid oxygen, liquid hydrogen, or methane, because they boil off. It's a hazardous operation.
The countdown starts. That meticulously planned sequence ticking down minute by minute, second by second.
Leading to ignition, T0, liftoff. The engines roar, the clamps release, and the rocket climbs, fighting gravity, punching through the atmosphere.
As it gains altitude and speed, the empty stages separate and fall away.
The upper stage then ignites, providing the final push needed to get the payload into the precise orbit.
Once it's high enough, outside the dense atmosphere, the fairing halves separate and fall away too, exposing the payload.
And finally, payload deployment. The satellite or spacecraft is released, sent on its way to begin its own mission.
But as you said earlier, that's not always the end of the rocket story these days. Reusability changes things. Phase 5. Post-launch and reusability.
Right. For rockets like Falcon 9 or what Starship and New Glenn are aiming for, the work isn't over when the payload separates. That first stage, the most expensive part, performs this incredible ballet.
Boost back burns, entry burns, steering with grid fins, deploying landing legs.
All to guide itself back through the atmosphere for a powered landing, either back near the launch site or out at sea on a drone ship. It's amazing engineering.
Rocket Lab's trying something different too, right?
Yeah.
Trying to catch their electron booster midair with a helicopter.
Yeah, another approach to recovery. The goal is the same, though.
Yeah.
Get the hardware back. Because then you can move into refurbishment.
Cleaning it up, inspecting everything meticulously, making any necessary repairs, refueling it, and getting it ready to fly again.
And that is the real key to drastically lowering launch costs. You're not throwing away the most complex and valuable part every time.
Of course, some stages are still expendable. They're designed to fall safely into designated remote ocean areas.
But the trend is definitely towards reuse where possible. It fundamentally shifts the economics.
Okay, so we've walked through the life of a single rocket, but making all that happen relies on this huge global network, this ecosystem of suppliers, manufacturers, infrastructure.
It's absolutely essential. No single company does everything in isolation. Let's dive into that.
Okay, key components. We talked about propulsion, the engines, the heart of the rocket.
Yeah, and the companies building them are specialists. SpaceX with Merlin and Raptor, Blue Origin with BE-4, Aerojet making engines like the RS-25 for NASA, Rocket Lab's Rutherford, ULA Sources engines. It's a complex web.
And making those engine parts, the turbopumps spinning incredibly fast, the injectors with tiny, precise holes, that demands extraordinary manufacturing capability.
And like we touched on, that's where things like advanced machining and 3D printing come in. Rocket Lab, for instance, prints a huge portion of their engine. It allows for complexity and potentially faster production.
Then there's the GNC systems, the brain and nervous system. Flight computers, sensors like gyroscopes and accelerometers, GPS receivers, and all the software tying it together.
This stuff has to be incredibly reliable. And think about the processing power needed for something like a propulsive landing sequence. It's immense. Plus, for missions beyond LEO, these components often need to be radiation hardened to survive in space long term.
Who makes these? Are there specialized suppliers?
Oh, yeah. There are companies that specialize just in guidance systems or specific types of sensors or radiation-hardened chips. It's a whole sub-industry.
And materials, we mentioned the main ones, aluminum, lithium, carbon composites, stainless steel. Sourcing and fabricating those specialized materials is another big part of the ecosystem.
Definitely. And it's not just the raw materials, but the companies that have the expertise to machine them, to form them, to weld or bond them correctly.
Which brings us to the manufacturing and production ecosystem itself. Precision seems to be the watchword.
Absolutely paramount. Rocket parts demand incredibly tight tolerances, often working with materials that are difficult to machine. You need specialized tools.
Like the ones from companies like Mazak you mentioned, supplying advanced machine tools globally.
Exactly, including things like hybrid machines that combine traditional cutting with additive manufacturing in one unit. And again, those quality standards, AS9100 and a DP cap, they flow down through the entire supply chain. Every supplier needs to meet them to ensure the final product is reliable. Traceability is key.
And this whole ecosystem is ramping up like crazy right now. The production boom is real.
It really is exploding. The numbers are stark. What was it? 259 launches globally in 2024, deploying almost 2,700 satellites. A record.
And the U.S. has a huge share of that, like 65%.
Look at SpaceX's cadence alone. You mentioned the numbers: 60 launches in 22, 96 in 23, 134 last year. And they were already way past halfway to their target of maybe 150, even 180 for 2025 by mid-year. That's launching roughly every other day.
And others are scaling up too. ULA aiming for 25 Vulcans a year, Rocket Lab making composite structures for Electron superfast, aiming for a 7-day turnaround.
What's driving it? Primarily, it's the sheer demand for satellites, especially these huge mega constellations like Starlink. They need hundreds, even thousands of launches to build out and maintain their networks.
Okay, so you've got all these high-precision parts being manufactured around the world. Now you have to assemble the rocket itself, and the two main ways to do that right: vertical versus horizontal integration.
That's right. It's a fundamental choice in how you set up your factory and launch site. Vertical integration is kind of the classic image.
Like NASA's VA at Kennedy Space Center.
Exactly. The vehicle assembly building, it's iconic for a reason. It's just enormous. The largest single-story building in the world by volume, I think, over 500 feet tall.
Wow. And it was built for Saturn V, used for the shuttle, now for SLS. It has these massive high bays where they can stack the rocket stages one on top of the other, just like it'll be on the pad.
Huge cranes, controlled environments. It's an incredible facility, but it requires massive infrastructure investment.
So what's the alternative? Horizontal integration.
Yep. Assemble the rocket lying down, basically, in a long hangar, often called a horizontal integration facility, or HIF. Then you transport it horizontally to the launch pad and use equipment to raise it vertical just before launch.
And lots of rockets use this method.
Oh, yeah. Many Russian rockets like Soyuz, European rockets like Ariane 6, Rocket Lab's Electron, and SpaceX's Falcon family are all assembled horizontally. The hangars are still huge, but generally less complex than a VB.
So it's a strategic choice based on the rocket design, launch rate, cost.
Absolutely. It impacts facility design, ground support equipment, transport logistics, maybe even the supply chain for certain components. Interestingly, SpaceX uses horizontal for Falcon, but has gone vertical for Starship assembly down at Starbase. So you can see companies choosing different approaches based on the specific vehicle.
Okay, assembling it is one thing, but getting all these massive, often delicate pieces from where they're made to the assembly building or launch site, that sounds like a nightmare. Logistics.
It's a huge, often underappreciated challenge. You're moving components the size of buildings sometimes that are also incredibly sensitive.
And you need specialized storage too, right? It's not just sticking it in a warehouse.
Definitely not. Propellants are hazardous, often cryogenic, needing insulated tanks, strict separation, safety protocols. Large stages might sit in the VAB or HIF temporarily, but sometimes you need dedicated climate-controlled storage. Our sources mentioned Atlas V solid motors stored at Camp Blanding, for instance.
And even smaller components,
Yeah.
avionics, sensors.
They need careful handling. Cool, dry, insulated storage, protected from static electricity, sometimes in special breathable containers. Again, safety is paramount, especially with hazardous materials potentially nearby. Fire suppression, earthing, all that.
Okay, so storage is handled. How do you move these things?
Multimodal transportation. You use whatever tool fits the job. Locally, at a place like Kennedy Space Center, you have those giant crawler transporters inching fully stacked rockets out to the pad.
Like mobile launch platforms almost.
Pretty much. Other places might use rail, like for Soyuz rockets moving to the pad in Baikonur or French Guiana. Barges are absolutely critical for really huge components that just won't fit on roads or rail.
Like the SLS core stage traveling on NASA's barge Pegasus from Louisiana to Florida.
Exactly. Or even using barges as landing platforms out at sea, like SpaceX does. Or like Rocket Lab plans for their Neutron rocket's first stage.
What about long distance? Or overseas?
That often means air cargo for high-value, time-sensitive parts like engines, maybe stages, or the satellites themselves. Using enormous cargo planes like the Antonov An-124, Boeing 747 freighters, or the Airbus Beluga. Specialized logistics providers handle this.
And sea transport.
Yep, for really big moves internationally. Arianespace actually has a dedicated ship, the Canopy, designed specifically to transport Ariane 6 stages from Europe to the launch site in South America. You also have concepts like air launch, where a rocket is carried aloft by a plane like Pegasus, or the mid-air recovery stuff.
And managing all this hardware, the testing, the launch, requires the nerve centers, the control rooms and tracking stations.
Absolutely. Mission control centers, whether it's NASA's famous one in Houston or the European Space Agency centers, or private ones like Astrobotic had for their lunar mission, they are the brain during the actual operation. Real-time command, telemetry monitoring.
And you need tracking stations all over the world, right? To keep tabs on the rocket as it ascends and then track objects in orbit.
Yeah, networks like the U.S. Space Surveillance Network constantly monitor space. And there are companies that provide the ground station technology, the flight dynamic software, the space situational awareness tools. Think Beyond Gravity or GMV.
And we can't forget the test facilities themselves as critical infrastructure. McGregor, Stennis, European sites like Lempolthausen in Germany, where the hardware gets proven out.
Even companies that just specialize in designing and building the complex test benches needed to simulate flight conditions, it's all part of this vast operational infrastructure.
Okay, so design, build, test, launch, recover. An incredible technical feat. But it all happens within a pretty strict framework of rules and regulations. That's another layer of complexity.
A huge layer, often invisible to the public, but absolutely critical. Getting permits and licenses is non-negotiable.
In the U.S., the main player is the FAA, the Federal Aviation Administration, right? For commercial space launches.
That's right. They license the launch itself, the launch site or spaceport, and even re-entry operations for reusable vehicles. They also issue experimental permits for R&D work, especially for reusable suborbital rockets.
And they set safety standards.
Very strict ones. The big one is limiting risk to the uninvolved public on the ground. The target is usually less than a 1 in a million chance of casualty per mission. Operators also have to show significant financial responsibility, usually meaning hundreds of millions of dollars in insurance coverage.
I heard the rules have been changing, trying to keep up with the industry.
Yeah, there was a major overhaul finalized around 2020, moving towards more performance-based regulations rather than prescriptive ones, trying to be flexible enough to accommodate new technologies like reusability and the sheer increase in launch cadence, while still maintaining safety.
What about smaller rockets, like hobbyists?
That's generally handled differently, often under organizations like the National Association of Rocketry, NAR. But once you get into high-power rocketry, you often need certifications and might need specific FAA waivers or airspace authorizations, depending on the altitude.
In Europe, is it fragmented country by country?
Traditionally, yes, but there's a big push for harmonization. The proposed EU Space Act, expected maybe 2025, aims to create a single, unified regulatory framework across the EU.
What's the goal there?
To simplify licensing, make Europe more competitive, reduce reliance on non-EU launch providers, and also standardize rules on important things like deorbiting spacecraft and environmental protection related to space activities. It ties into ensuring Europe has its own guaranteed way to space, especially with Ariane 6 coming online.
Okay, so rules for launching. What about rules for actually making the stuff?
Well, yeah. Manufacturing is regulated too. A big one in the U.S. is ITAR, International Traffic in Arms Regulation.
How does that apply?
Because rockets and related technologies are considered defense articles, ITAR controls the export of not just the hardware, but also the technical data. Blueprints, CAD files, analysis reports. Companies have to be extremely careful about who has access to this information, even internally or with suppliers, especially overseas suppliers, to avoid what's called a deemed export. It adds complexity to global supply chains.
And we already talked about the quality standards like AS9100 and NADCAP. Are those regulatory?
They're industry standards, but they're often mandated by contracts, especially for government missions, and are effectively required to ensure the necessary reliability and safety. So yes, they function like regulations in practice. Precision, traceability, security, it's all baked in.
Okay, rules for launch, rules for making. What about the environment? Launching rockets seems like it would have an impact.
It definitely does, and that's increasingly a focus of regulation and concern. In the U.S., the National Environmental Policy Act, NEPA, applies. The FAA has to conduct environmental assessments, or sometimes more detailed environmental impact statements, before licensing launches or spaceports.
And that involves looking at
Potential impacts. Rocket emissions are one area. Different fuels have different byproducts. Kerosene-based fuels produce CO2 and black carbon, or SIT. While the total carbon footprint of the launch industry is currently small globally, that soot deposited high in the stratosphere is a concern for atmospheric warming.
what about hydrogen-fueled rockets? They're cleaner, right? Just water vapor?
Mostly water vapor, yes.
Huh?
But large amounts of water vapor injected directly into the normally very dry stratosphere can also potentially impact atmospheric chemistry, including ozone depletion. Other pollutants, like nitrogen oxides or chlorine compounds, can also be released depending on the fuel and engine type.
And impacts at the launch site itself.
Yeah, potential contamination. Some propellants, like hydrazine, are highly toxic. Unburned fuel, heavy metals from engine components. These can potentially contaminate soil and water, especially at coastal launch sites. Noise pollution is also a factor during launches.
What about the waste from manufacturing? Making all these exotic parts must generate some nasty stuff.
It can. Solvents, heavy metals from machining, volatile organic compounds, VOCs, silica dust from composites. Manufacturing generates hazardous waste that's regulated under laws like the Resource Conservation and Recovery Act, RCRA, in the U.S., dictating how it must be handled and disposed of safely.
And then there's the issue that gets a lot of attention lately, orbital debris, space junk.
A huge and growing problem. Once something is launched, especially into LEO, it can stay up there for years, decades, even centuries if it's high enough. And collisions create more debris.
Are there international laws about cleaning it up?
That's the tricky part. There's no single binding international treaty specifically governing debris mitigation or removal. Existing space treaties were written before debris was a major concern, and they deal more with liability and ownership, which actually complicates active removal. You can't just grab someone else's dead satellite without permission.
So what is being done?
There's been U.S. policy focused on debris mitigation since the late 80s. More recently, both the FAA and the FCC in the U.S. have proposed or enacted stricter rules for commercial operators,
Like what?
requiring concrete plans for disposing of upper stages and satellites at end of life. The FCC now requires most new satellites licensed after September 2024 to be deorbited within 5 years of mission completion. The FAA proposed rules pushing for specific disposal methods, controlled re-entry over remote ocean areas, moving to a graveyard orbit far away, boosting to an escape trajectory, or ensuring active removal within 5 years, with strict limits on uncontrolled re-entries.
But these are U.S. rules, not global.
Primarily U.S. domestic rules for their licensees, yes. There are international guidelines, like from the UN Committee on the Peaceful Uses of Outer Space, UNCO-UOS, but they're largely voluntary. Many experts agree that binding international norms are needed.
Is the industry itself doing anything?
Yes, definitely. There's work on developing cleaner propellants like methane or green hydrogen produced renewably, efforts to reduce waste in manufacturing, and several projects, some government funded like ESA's Clear Space One mission, some private, are developing technologies for actively removing existing large pieces of debris. But it's a complex technical and legal challenge.
Wow. Okay, so putting that all together, it's just staggering, the sheer complexity.
It really is. You go from that initial concept, that spark of an idea, through incredibly intricate design.
To manufacturing parts with almost unbelievable precision, using materials and processes pushed to the absolute limit.
Assembling it all, testing it relentlessly, making sure every single system works perfectly.
Managing a global supply chain, coordinating logistics that move mountains, basically.
And navigating this dense web of regulations covering safety, national security, international agreements, and environmental protection, both here on Earth and in orbit.
It really is a pinnacle of human engineering and, maybe just as importantly, human collaboration and organization.
Absolutely. And when you understand even a little bit about all those thousands of steps, the tens of thousands of people involved across countless companies and agencies, the specialized facilities, the rigorous checks, you just can't look at a rocket launch the same way again.
No, it gives you a whole new level of appreciation for what that fiery ascent actually represents. Every single launch is an achievement.
It truly is.
So here's something to think about as we wrap up. We're seeing this explosion in launch activity, this relentless drive for lower costs through reusability, and at the same time, growing awareness and concern about the environmental footprint both on Earth and the growing hazard of orbital debris. How do we balance that push for ever greater access to space with the crucial need to be responsible stewards? Stewards of Earth's environment, yes, but also stewards of the space environment itself, keeping it usable for generations to come. Is the next big leap needed in technology, or is it really about policy and cooperation?